Okay, so let us begin with a quick recap. There is also a minor bug in notation which I will fix and in this recap itself. Okay. So, the basic problem we are dealing with here is coded modulation. Okay, so the last time I was talking in at length about why this is different from simple error correction and why people moved to this coded modulation idea and how it is implementable today in systems and what are the possible benefits. Okay, so we did not really quantify the benefits, maybe we will quantify that in this lecture. Okay. So, what is the picture now? The picture basically looks like this. You have a k-bit message M which gets encoded by an, let us say, using an n comma k code. Okay, so something is going on here. N comma k code. Okay, so suddenly I seem to be having difficulty writing. So, let me rewrite again. Sorry about that. Okay. Okay, you have an nk code which converts this into a code word of n bits. Okay. And then the difference is we will also consider the modulation block which converts bits into what I am going to call as symbols. Essentially these symbols represent, I think we used S. Okay. So, these symbols represent signals that are going into the channel. Okay. So, you use a basis for those signals and decompose it, and we will use only a simple one dimensional situation. So, you have BPSK which takes 0 to +1. Oh my god, suddenly this touch screen is behaving in a peculiar fashion. Okay, let us say 0 goes to +1 and 1 goes to -1. Okay. So, this is my simple BPSK conversion. To this I am adding Gaussian noise which is normal with mean 0 and variance sigma square, and it is IID. Okay. And we get a received vector R, and essentially in coded modulation we will run a decoder that works on R. And produces, let us say, a C cap, okay, an estimate of C. Okay. So, this is the idea. So, your decoder works with a real valued vector as opposed to what we had before, which was essentially a binary vector, okay, or say a vector over GFQ or GFP to the M or something. Okay. So, that is a big difference. Okay. And basically we distinguish between two cases. One was the, okay, so I think okay. So, one was the hard decision situation. Okay. And then the others were soft decision. So, I do not know if my handwriting has become bad or it's, or if the screen is trying to be too smart. Is there like a piece of cloth I can rub the, I think it is wet, because of that I am having some difficulty. Usually it is not so bad, I can write and it is a little bit legible. So, I am going to use my maybe handkerchief and clean this screen, presumably that is the problem. Okay, so usually it is not, sure you guys agree, no, it is not this bad, right? It is not the most good looking handwriting out there, but it is not terrible from a legitimate, I mean being legible point of view. Okay. So, we distinguish between two cases, hard decision and soft decision. Okay. So, on hard decision the first block that you do after you receive R is what I called a slicer. Okay, so you slice it, and this is a symbol by symbol slicer, okay, and you produce some kind of an estimate of S cap, which is basically equivalent to, right, some what I called as W, and this W was basically from C you can have a binary symmetric channel and you can get W, right. So, that was the idea. So, you S cap would be a symbol, it will be +1 or -1, from +1 you go to 0 and -1 you go to 1. Okay. So, this is basically inverse BPSK. You do inverse BPSK, you are only simulating a binary symmetric channel, and then you run your classical syndrome decoder on this. Okay. You run a syndrome decoder, it's ML, it's an ML decoder for the binary symmetric channel, and you get a C hat. Okay. So, this is hard decision, but clearly you can see already that it is suboptimal, because even though the vector R is not IID, okay, it is not IID, this is treating it as IID, at least for the slicing point of view, from a slicing point of view. Okay. You should not be slicing it, but it is slicing it. Okay. So, this is the hard decision decoder. In soft decision, we at this point we think in last class we defined ML decoder, which minimizes the block error probability that C is not equal to C cap. Okay. And I showed the equivalence in BPSK over AWGN, ML decoder is equivalent to minimizing Euclidean distance. Okay. So, I am briefly sketching this. So, hopefully you remember what it is. Euclidean distance between R and 1 minus 2u. Okay. So, that is what the ML decoder is, and this is true in general, and for the BPSK case you can also show this is the same as maximizing the dot product between R and 1 minus 2u. Okay. So, those are various versions of the ML decoder, but I quickly pointed out, I gave you a slightly non-trivial example, and I kind of pointed out that it is going to become very difficult as n becomes large. Okay. So, you are going to get n and k becomes large, you have to do a lot of correlations, lot of computations, completely impractical to implement. Okay. So, you can't do that. Okay. So, of course, what is actually implemented in practice oftentimes is an approximate soft decision decoder. Okay. So, something for which you can't prove any optimality results, but you can analyze it maybe in some manner, you can analyze it in some approximate manner, you can analyze it and show using simulations that it works very well. Okay. So, that is how people do today. Okay. So, it seems like a pretty ad hoc solution to an engineering problem, but that is pretty much how these approximate soft decoders are studied. Okay. So, that is something to keep in mind, but before that we have to definitely see the optimal decoders. Okay. So, know what the optimal stuff is before you go ahead and approximate it. Okay. Otherwise, you will never continuing to approximate without knowing whether there is anything optimal out there or not. Okay. So, the next type of optimality, which I said is slightly easier to get to in practice, is the bitwise MAP decoders. Okay. Bitwise optimal decoders. So, in this case you think of your decoder working on R as producing some vector B and the goal is to minimize probability that Ci is not equal to Bi. Okay. What is Ci? Ci is the code word, transmitted code word. Okay. So, I was so this is kind of where we stopped, or we did this towards the end of last class, and I made a mistake in the notation. So, I am going to correct that now. Okay. So, I was able to claim that this would be the same as what? So, I made a claim which we did not prove, but I think it is quite easy if you go through the whole analysis. This is the same as maximizing what? I mean, no, I think maybe I approached it a little bit differently. I think I approached it a little bit differently. So let me just do that once again. Sorry about that. So I said basically to do this, you have to say Bi is 0 if probability that Bi or Ci, sorry, that's where I made a mistake. I put Bi inside, I should have put Ci there. Okay, Ci equals 0 given the entire vector R is greater than probability that Ci equal to 1 given the entire vector R. Okay, so this is the rule which I said is equivalent to this. Okay, so that you can prove using some very basic analysis. I am not going to do it. It is kind of intuitive and clear that that is what you should do. Okay, if you compute a probability that is greater, you decide Bi is 0. Okay, and you decide Bi equal to 1 otherwise. Okay, so quite a simple rule. And then we defined, we modified this rule. We looked at several equivalent ways of doing it. And one thing I claimed was this is the same as probability that Ci equals 0 given R is greater than half. Okay, it is the same as that. Okay, that is a very easy thing to see. And this is also the same as the what I called as the likelihood ratio, which is f of R given Ci is 0 divided by, is there a question? It is okay. F of R given Ci is 1 is greater than 1. Okay. So, in this step you have to assume equally likely messages. Okay. So, you have to say C is equally likely. Okay. So, that is important, and also you have to also make the assumption that the code is a code does not have some trivial constructions. I mean, the code you should not have one bit which is always 0. Okay, so that is a very weird construction to have. No, I mean, you should not have that. As long as you do not have that, this is okay. Okay, so this is good enough. And this I called as the, what did I call this? This was the vector likelihood ratio for the ith bit. Okay, so vector because we are looking at the entire vector R. This is likelihood ratio. This is for the ith bit. Because it is Ci. Okay, so I think this is pretty much where we stopped in the last lecture. So this is a good point to continue once again. So are there any questions on this? This is reasonably clear. Yeah, something like that. Okay, so the question was, is the outcome guaranteed to be a code word? I made a comment yesterday that the outcome need not be a code word. Okay, so this B need not necessarily be a code word, but if you are doing systematic encoding, clearly the first k bits of this out vector B, you can take it as your message, decoded message. Okay, so that is okay. It is not a problem. You can always do that, but the output is definitely not guaranteed to be a code word. That is not the rule that I am using. Okay, so in the rule, I am only trying to minimize probability that Ci is not equal to Ba. Okay, so I am not trying to force the constraint that the vector B has to be from some set. I am doing it just bit by bit, okay, without any other constraint.
Sir, how is this different from hard decision?
How is it different from? How is what different from hard decision?
The result from this will be different from hard decision.
Yeah, the R here is the continuous real valued vector that you receive. Okay, so the question was, why is this different from hard decision? Okay, so maybe as I do it, and we will see an example, and you will see clearly it is not hard decision, but before that, even I am a little bit confused about why you are asking me this question. Why do you think it should be same as the hard decision?
Won't it depend just on that ith bit?
What depend just on R? F of the entire vector R given Ci. Okay, how many of you think the f of entire vector R given Ci will depend only on the ith bit? What do you mean by depending on the ith bit? Okay.
RI is affected by CA.
No, R and C don't have the same dimensions, right?
Okay, so the question is, suppose I is 1, okay, I is 1, I am looking at C1. R1, is it affected only by C1, or let us say is R2 not affected by C1? Let me ask that question. Is that question true or not? Okay, you have to think about it. Let us say you go from R1 to RK and then you go to RK plus 1, okay, right. One can argue that R1 through RK maybe is affected only by the C1s if you do systematic encoding. You are picking C1 through CK independently, but definitely RK plus 1 will depend on all C1 through CK. Okay, RK plus 2 will depend on C1 through CK again. Okay, it will depend also on CK plus 1. Given CK plus 1, obviously it will not depend on anything else. Okay, but I am not giving CK plus 1 here, I am only giving CI. Okay. So we will write down precise expressions here. I mean, this is an important question because most people who see it for the first time get confused by this. Okay, this is the standard thing in probability, difference between conditional independence and independence. Okay, so two random variables or two events can be conditionally independent given some other event, but in totality they may not be independent at all. So this is one of those cases. Okay, so clearly it happens.
So we look at the entire R.
Yes,
And
that's
not
what I
just
mean.
the sampled value of R at that. So just like over the entire
Okay, Ri you mean when you say sampled value of R at that time. So Ri, yeah, you are not looking at R, this is entire vector R. That is why I have once again emphasized this is vector likelihood ratio. I am sorry? Yeah, how do we compute it? Let us see. I mean, you know all the probability tools to compute this, but I will do it explicitly in some examples, and in general also we will do it. Okay, so we will do it, we will see how to compute it. But the question that you are asking is important. Okay, so Ri, doesn't it depend only on Ci? You should ask. I mean, that's a question that you should ask. It's true. Okay, so it depends on Ci. So given Ci, Ri does not depend on any other code word bit. Okay, that is true given Ci. But no, let me complete this. It's very important. Let's say Ri does not depend on any other Cj given Ci. Right? Is that true? Okay, so that's something that's important. But now we have done. If you look at the entire vector R given Ci, you can't say the entire vector is independent of everything else because you have so many other things also, right? So that's what you have to look at very carefully and be sure about. Okay, so given Ci alone does not make all the R's independent. Does not happen. If you are given the entire code word, then all the R's are independent, but only Ci is given and all the vectors, all the values in R do not become independent. Okay, think about it for a while. It's an important thing to be convinced about because the entire decoder hinges on that. Okay. Anyway, when I write down the expression, it will be more clear to you. We will write an explicit expression for this, and you will see clearly some values terms will occur which are not independent, and you will see how it works out. Okay. So let us write that down. So let us take a very simple example first and then write this expression, and then we will go on and see more complicated examples, and then I will write the most general form of it. It's very easy, it's very basic elementary probability, but it's a bit confusing. Okay, so that's why you should see this very carefully. So in the example, we will take the first the 3,1 repetition code. Okay, all right. So let us try to write down f of R given C1 equals 0 divided by f of R given C1 equals 1. Okay. So here you will get a slightly different answer which is not general, but anyway let me just write it down and then I will see something more a bit more different. Okay. So remember R is a general vector R1, R2, R3. Okay. How do you evaluate this probability is important. Okay, how will I write the numerator? What can I use to, how can I express the numerator in any terms?
So can we make use of our knowledge that C2, C3 will also be equal to
Of course you have to make use of the knowledge. Okay, so that's the only knowledge you have, you don't have any other knowledge, right? Okay, so C1 is 0 implies what, C2 is also 0, C3 is also 0. Okay, so it is a very simple code. Okay. So C1 is 0 means the entire code word was 0 0 0. So the way you write this is basically you have to say this is probability that C equals 0 0 0 given C1 equals 0, which is actually 1, but anyway I am writing it down just to show you how it works, times f of r given C equals 0 0 0. Okay, so that is how you write the numerator. See, from C1 you go to C, because C1 is 0, C is constrained to be, so let me write it down, I am sorry, let me write down the whole thing, then we will see how it works, I am sorry. So basically the best way of writing it is, so you have to say probability that C equals 0 0 0 given C1 equals 0 times f of r given C equals 0 0 0 plus probability that C equals 1 1 1 given C1 is 0 f of r given C equals 1 1 1. Okay, and then in the denominator you write a very similar expression. Okay. So what is happening is C1 is given, C1 is 0 or C1 is 1, from C1 you have to go to C, there is a probability there, okay, and then from C you have to go to R. Okay, from C1 you are going to the vector C, and then from C you are going to the vector R. Okay. So the probability distribution from going from the vector C to the vector R is well known to you, it is all independent, it is product of several Gaussians. What is the probability distribution from going from C1 to the vector C? That is where the knowledge of the code comes in, okay, right. If C1 is 0, what do I know about this probabilities? This guy is 0 and this guy is 1, okay. Likewise here this guy is 0 and this guy is 1, okay. That is where I use my knowledge of the code, okay. In a more complicated situation there will be more terms coming in here, okay. Here it is just only one term, it is a very trivial code, so you get the answer very easily. Okay. So this basically becomes f of r given C equals 0 0 0 divided by f of r given C equals 1 1 1. Okay. Now some of you will argue I can directly write this without any, in this case it seems like a very simple step. I agree with you, it is simple in this case, but I wrote this down in such a laborious fashion because the same formula can be repeated for any code. Okay, and we will see the probability there will change, it is very easy to do that. Okay, so what is this expression? You know now that R has become conditionally independent, you have given all the code word bits, so the vectors of R has now become conditionally independent, so you simply multiply the exponentials that you get from the Gaussian distribution. Okay, the constants are going to cancel in the numerator and denominator, so you only have to worry about what is in the exponent, and the exponent also you know how it is going to look, right. It is simply going to be the distance between r and 1 1 1 and r and minus 1 minus 1 minus 1. Okay, so that is what you will get. So essentially this is going to be e power minus r minus 1 1 1 squared divided by 2 sigma square, the whole thing divided by e power minus 1 minus 1 minus 1. Is that okay? Is it okay?
Simple.
By 2 sigma square. Is that okay? So I have an explicit formula for my vector likelihood ratio in terms of the received vector r. Okay, so once you give me an r, I will go plug it in, compute this, okay, and see which is whether it is greater than 1 or not. Okay, in fact, we can simplify this a little bit more. Okay, after all, this is just a square, right? Sum of square. If you simplify it a little bit more, Let us see what you get in this case. Okay, you can show f of r given C1 is 0 divided by f of r given C1 is 1 will work out to what? If you do the simplification, show it will become e power 2 by sigma square times r1 plus r2 plus r3. Okay, you can do that work. It is just basic algebra. See, you can cancel it out and subtract it, and you will get this answer. Okay, 2 by sigma square into r1 plus r2 plus r3. Okay. So, one thing you are noticing when you do these likelihood ratios is everything is e power something, right. So, it makes a lot of sense to take logarithms for the likelihood ratio. Okay. Anyway, you are going to only check if this is greater than 1 or less than 1. Okay. So, you might as well take logarithms and see if it is greater than 0 or less than 0. Okay. So, it will be totally equivalent. So, that is why people usually use the log likelihood ratio as opposed to just the likelihood ratio for doing anything. Okay. So, we will first define this vector log likelihood ratio. Okay, which is basically in a general setting, it is this log likelihood ratio is abbreviated as LLR. Okay. So, this vector LLR will be log of f of r given Ci is 0 divided by f of r given Ci is 1. Okay. So, we can call it, maybe since it is a vector, we will call it capital Li. Okay. So, this is the vector LLR for the ith bit, okay, using the ith bit. Okay. So, in fact, for the repetition code, if I change the C1 to C2, what will happen? Won't make any difference, because all the 3 bits are the same, you will get the exact same answer. Okay. So, for the repetition code, all the 3 vector likelihoods are exactly the same and they are all equal to this. Okay. So, for the 3-1 repetition code, capital L1 equals capital L2 equals capital L3 equals 2 by sigma squared times R1 plus R2 plus R3. Okay. And how do I decide on the particular bit? I simply see if this quantity is greater than 0 or less than 0. What do we have here actually? The same as ML. Okay. So, for the repetition code, the bitwise optimal decoder matches with the ML decoder. So, it will definitely only output a code word. Okay. So, you do not have to worry about it. So, it is a good code in that sense, okay. But we will see other codes are not guaranteed to do such things. Okay. So, we will have all kinds of other answers. Okay. So, the repetition code, the 3-1 repetition code, bitwise MAP decoder is the same as the ML decoder. Okay. So, the condition here is either this is greater than 0 or less than 0. Okay. Okay. So, I want to take a slightly more complicated situation, and let us go back to our standard example. I want to do the 6-3 example. I know it is a little bit more complicated, but I think it is just within reach of working by hand, and it will really illustrate some of the ideas that are crucial. Okay. So, let us see the 6-3 example. Let me see, we really need the list of code words. So, let me try and do this off the top of my head. I think it is 110100, am I right? 101010 and then 011001, then 410, then 0 0 1 1,
1 0 1 1 0
1 0 1 1 0 1, and finally 0 0 0 1 1 1. Am I right? So, this is the 6,3 code. Okay, this is the same code that we have been using all along from day 1, I think maybe we are using this code. So, let us try and write down some expressions here. So, remember again we are going to think of the last 3 bits as the systematic bits. Okay. So, it makes sense to try and compute L4. Okay. Yes or no? Okay, so when I do bitwise MAP decoder, it is enough if I find the message bits, right. Why will I bother finding the parity bits? It is a good question to ask, but maybe you should worry about parity bits also. But if you are going to implement the bitwise MAP decoder brute force by computing the expression fully, you do not really have to find the parity bits, just find the message bits. Okay. So, if you want to find the parity bits, you simply do an encoding again with the message bits you found, you can find the parity bits. If you want, I mean that is another way of doing things, which is guaranteed to give you a code word, by the way. So, that is one more way of thinking about it. Okay, so, let us do L4, and L4 remember is f of r given. So, once again I mean the setting, I am not repeating the setting, it is always the same. You are doing BPSK AWGN and you get a received vector r, which in this case will have 6 different coordinates, right, r1, r2, r3, r4, r5, r6. Okay, so now I am asking this question. Okay, so there is a logarithm in front of this. I have to really erase it and write it again. Sorry about that. Log. Okay, this log will usually take as log base e. Okay, so remember that it's logarithm base e. That's why the e power just goes away. Okay, so f of r given C4 is 0 divided by f of r given C4 is 1. Okay. So, now when I do the computation, right, you will not simply get a 0 1 like you had before. You will have multiple expressions in the numerator and multiple expressions in the denominator. Okay. So, you have to pay attention to that. So, let's just write this ratio, okay, and then we will take the logarithm finally. Okay. So, it is not a big deal. So, the likelihood ratio becomes, okay, so there will be probability that C equals, okay, what are the possibilities for C given that C4 is 0? Okay, so you have this guy, this one, and this one. Okay, so it's enough if you only look at these 4 possibilities, and you can also assume all those are equally likely. Okay, because I said the message, all the code words are equally likely. So, you can assume these 4 are equally likely. Okay. The others will have probability 0. So, each of these 4 will have probability 1/4. Okay.
Always 2 power k minus 1 terms will be there.
Yeah, that's true. That's true. So, we will come to that slowly enough. Okay. So people are making some comments about what will happen in the general situation. I am glad you are thinking about that, but let us first do this and then we will go to that. Okay. Be a little bit more patient. Okay. So, you have to write down, I will write the first numerator alone in full expansion in a boring way, and then we will simplify and quickly write the final answer. Okay. So, the first expression given C4 is 0 times f of r given, I will write 0 0 0 0 0 0 plus probability that C is 1 0 1 0 1 0 given times f of r given C equals 1 0 1 0 1 0 plus probability that C equals 0 1 1 0 0 1 given C4 is 0 times f of r given 0 1 1 0 0 1 plus probability that C equals. So, this is the numerator, remember, C equals 1 1 0 0 1 1 given C4 is 0 times f of r given 1 1 0 0 1 1. Okay, so, this is how the numerator will look, and each of these terms will have probability 1 by 4. Okay. So, likewise when you write the denominator, you will have how many possibilities? 4 possibilities. What are the possibilities that show up in the denominator? 1, 2, 3, 4, exactly the other 4. Okay. Exactly the other 4 will show up, and once again you will have the 1/4, 1/4, 1/4, 1/4 multiplying the conditional PDFs. Okay. So, you can cancel all those 1/4s away when you take the ratio and write an expression only involving the conditional PDFs. In the numerator there will be 4 terms, and then in the denominator there will be the 4 other terms. Is that okay? All right. So, that is what I am going to do in the next page, but then I will have to remember the code. Okay. So, hopefully I will remember. Let us see. If I do not remember, I will come back and fix it. Okay. So, let us try some of the more fancy. I think this is supposed to work. Let me see. Let me try some of the more fancy. There you go. Copy. There you go. It's not bad at all, huh? Okay. So that's the code. So L4 then becomes, okay, so let me write this down, f of r given 0 0 0 0 0 0, f of r given 1 0 1 0 1 0 plus f of r given 0 1 1 0 0 1 plus f of r given 1 1 0 0 1 1. Is that okay? So that's the numerator. Then the denominator you will have f of r. Okay, so log I forgot. Okay, so as usual, thanks for reminding me. So L4 is, there is a log, and then you have r given 1 1 0 1 0 0 plus f of r given 0 1 1 1 0 plus f of r given 1 0 1 1 0 1 0 0 0 1 1 1. Okay, so all this is a bit boring, and I want to also emphasize the fact that doing optimal bitwise soft decoders and all quite boring exercises. Okay, it's not so easy. You have to look at all possibilities. Even so, this is just for the 6.3 code. Imagine what will happen if you do 1000,500 code. Okay, so it's just impossible. Okay, these exercises are very difficult. Okay, and the approximate methods that we'll introduce later, well, they'll do these things in an iterative manner approximately, and that turns out to be good enough. Okay, so keep that in mind. Okay, so don't lose hope as we write these painful expressions, but there is some light at the end of the tunnel. Okay, okay, so remember each of these expressions. How will each of these expressions look like? It will be a product of several Gaussians, right? And because it's R becomes conditionally independent once you give the code word. Okay, okay. So what we can do, there is a nice bit of trickery you can do here. I mean, it's not very great. It's still the expression is still messy, but at least you will write it in some other terms which will give you a lot of intuition about how this is working. Okay, so maybe it will give you some intuition. Okay, so what you do is you divide numerator and denominator by this term. Okay, I know all of you are going to object that this is not a code word. Okay, I know this is not a code word, but this is some expression, and I can definitely divide numerator and denominator by this expression. Okay, so nothing stops me from doing that. So divide each term by this expression. Okay, so what you will get is whenever there is a 1, what will happen to that term? It will cancel it out. Okay, whenever there is a 0, it will divide by that corresponding received value given 1. Okay, so what you will get effectively when you divide by this is you will get the scalar log likelihood ratios in the numerator and denominator always. Okay, So, you will get an expression where you are going from the scalar log likelihood ratios or scalar likelihood ratios to the vector likelihood ratio. Okay. So, I am going to show how that happens here. So, maybe for one term and then you will see for how it works in general. Okay. So, let us pick this term here and divide by this and see what happens. Okay. So, f of r given 1 0 1 0 1 0 divided by f of r given 1 1 1 1 1 1. Okay. So, this is going to be the constant I will ignore. Okay. So, it's anyway gets we have gotten rid of it. This will be e power minus r 1 plus 1 squared by 2 sigma squared times e power minus r 2 minus 1 squared by 2 sigma square times e power minus r 3 plus 1 squared by 2 sigma square. I am going to run out of room. Whenever I run out of room, I will stop. Okay. So, hopefully, you can extrapolate what is there. Okay. So, r 4 minus 1 squared by 2 sigma square, and then you will have 2 other terms. Okay. I am not writing the 2 other terms. Okay. So, there will be some 2 other terms. Okay. You can imagine what those 2 other terms will be. Then you are dividing by what? E power minus r 1 plus 1 whole squared by 2 sigma square times e power r 2 plus 1 whole squared by 2 sigma square e power minus. Okay. So, there are various other ways of writing it, but anyway. So, let me just go through this painfully first time and then okay. So, you see clearly there is some cancellation. Whenever you have a 1, it will cancel. Okay. Whenever you have a 0, it will not cancel. Okay. So, essentially another way of writing this, which will maybe simplify things a lot, is f of, let me write down the same expression again in a slightly different way, f of r given 1 0 1, what was the expression? I am sorry. Okay, 1 0 1 0 1 0 divided by f of r given 1 1 1 1 1 1. This is basically the product f of r I given what? Okay. So, I such that C I is 0, okay, I such that C I is 0. Suppose this vector is some C, okay, f of r I given 0, right. Then you also have a product I such that C I is 1 f of r I given 1, right. In the denominator, what do you have? All of them are 1s, right. So, product over all I. Okay. So, let me write it down also just like that, even though the denominator is different, I will write it r I given 1. Okay. So, this is essentially what is happening here. Okay. So, remember what is this notation? It is clear, right, what this notation is. It is basically that expression e power 1 by root 2 pi sigma. So, that is what you will get 1 by root 2 pi sigma e power minus r I plus 1 squared by 2 sigma squared. So, that is the expression. Okay. So, clearly what will happen is these cases will cancel. Wherever you have 1s, that term will cancel, and wherever you have 0, you will get this ratio now, new ratio, which is again a likelihood ratio of only the scalar r I given C I. Okay. So, that is what you get. So, essentially what you get here is product of I such that C I is 0, this ratio f of r I given C I is 0 divided by f of r I given C I is 1. Okay. So, this quantity we will call as small l I, which is the, okay, now this quantity we will call as e power small l I, okay, so which is basically the scalar likelihood ratio, okay, and then I will denote as l I the logarithm of this. Okay. So, that is what I am going to do. of Ri given Ci. Okay, so that is important. But I am talking only about Ri now. Okay, given Ci. Ri just depends on Ci, nothing else. Is that okay? So, I know I am beating about this, laboring this point a little bit, but I think it is important that you see that the vector log likelihood ratio depends only on the scalar log likelihood ratios and nothing else. Okay, so the ratios is what will matter. Okay, so let's introduce this notation. We will use the scalar LLR, okay, which is basically small li. It is the logarithm of f of Ri given Ci is 0 divided by f of Ri given Ci is 1. Okay. So, for BPSK over AWGN, it will cancel very nicely. Okay. What will happen for BPSK over AWGN? This product will simply be e power minus Ri minus 1 whole squared by 2 sigma squared divided by e power Ri plus 1 whole squared by 2 sigma square. This will basically become e power 2 r by sigma squared. Okay, so you can simplify 2 Ri by sigma squared. Okay, is that okay? So, for BPSK over AWGN, okay, I am not able to write suddenly. Let me try once again. For BPSK over AWGN, okay, it is not working. The mouse seems to be working, but the okay, did somebody do something here? Actually, it is not even coming down here, I do not know why, it just stops there. Can you see that? It is stopping there, it is not coming down below this. Have to restart? Mouse button properly. Okay, all right. So it works out like this. So, when you take logarithm, what will happen? You will get 2 Ri by sigma square. So, for BPSK over AWGN, the scalar LLRs have this very simple expression, which is 2 Ri by sigma square. Okay, the ith received value, you simply scale it by 2 by sigma square, you get the scalar log likelihood ratio. Okay, so remember this is only for the ith position given the ith bit. Okay, Ri given Ci, that is all. Okay, what you really want is the vector LLRs. Okay, that is what you really want. Okay, if you have that, then you can make a decision on the ith bit. Okay, right. So, now there was a question about why is this bitwise MAP different from hard decision decoding. In hard decision decoding, you use the scalar LLRs to make decisions on each bit, but that is not your final decision, it is only a tentative decision, because after that you are again going to do a syndrome decoding. Okay, but in bitwise MAP you do not even do that, you do not even make a decision first and then do syndrome decoding, you directly compute the vector LLR and then use that to find the decision on the bit. Okay, clearly finding the vector LLR, you saw how messy the expression is, it is not the same as doing syndrome decoding after scalar LLR quantization. Okay, so it will not be the same, you can see that it is not the same. Okay, all right. So let us go through this previous example, use this idea of scalar LLRs and then try and write down the entire expression. Okay, so let me see if it has the code in memory, it still has it. Okay, so if I want to write L4, okay, I know I have to worry about code words with 4th position 0 in the numerator and then code words with 4th position 1 in the denominator, but then I am going to divide by something to make everything into LLRs, right. So that is what I am going to do. So all I have to do is something like this, I will take logarithms, okay, Whenever I have 0, I should have a e power small li term. Whenever I have a 1, I do not have to have that, right. That is how each of the terms will look like. Okay. So, I am going to write down the final expression. It will be like this, e power, the first one will be what? All the terms will come, right. So, that will be L1 plus L2 plus L3 plus L4 plus L5 plus L6. Okay, what about the next term? E power L2 plus L4 plus L6. What about the next term? E power L1 plus L4 plus L5. What about the last term? E power L3 L4. Okay, then you divide. Is that okay? What do you get in the denominator? E power L3 L5 L6 plus e power L1 L6 plus e power L2 L4 plus e power L1 L2. Oh, I think I should put plus, no, I am sorry, forgetting the plus everywhere. L1 plus L2 plus L3. Okay. Is that okay? So, one thing you notice is e power L4 occurs in every term in the numerator. Okay. In fact, that will happen always. If I compute some capital Li, e power small li will show up in every term in the numerator, because I am including only those code words which have Ci equals 0 in the numerator. So, clearly that term will show up in every single term. So, I can pull out e power L4, and then I have log of AB, which is log A plus log B. Log of e power L4 is simply small L4. Okay. So, you will get, if you do that simplification here, small L4 plus log of something. Okay. What will be that something? You can write that down. So, I am going to write it down once again just to be plus e power L2 plus L6 plus e power L1 plus L5 e power L3 plus L4 divided by e power. So, okay, denominator does not change. Okay, thank you very much. Plus e power L1 plus L6 plus e power L2 plus L4 plus e power L1 plus L2 plus L3. Okay. All right. Okay, so this expression to me brings out a lot of nice properties about the bitwise MAP decoder. Okay, and in fact, this expression is also general. If I, instead of 4, if I put 5, what will happen here? I will definitely get a small L5 plus log some numerator, some denominator, 4 terms in the numerator, 4 terms in the denominator, several e power L sums. Okay, so that is how it will look in general. This is a general thing. Okay, so we will also generalize it soon enough, and I will write a very general looking expression. You will see that this is true. Okay, so this is some kind of a scalar LLR. This is the vector LLR. Okay, so when you compute the vector LLR accurately, the scalar LLR is the starting point. Okay, so it is some kind of an intrinsic information. This thing is also called intrinsic information. Okay, so saying scalar LLR, we can say this is intrinsic or channel information. Okay, so this is, in fact, L4 has nothing to do with the code itself. Okay, right? You are looking at R4 and computing the likelihood for C4 without taking into account the coding at all. So, it is just intrinsic to that channel, whatever the channel is telling you about C4. Okay, at that point you are only using the channel information. Okay. Likewise, you have all the small l's, which are all intrinsic channel informations about each of those bits. You have to combine them in this peculiar way, not peculiar, well, straightforward way, you can say straightforward, but it is a complicated way to get the capital L4, which is really what you want, which is the your decision statistic. Okay, based on that you make a decision. Okay, and this combination is obviously very complicated, and there is clearly no easy way to see that this is the same as hard decision decoding, right. So obviously it won't be. If I say it won't be, you will believe me, right. If I say it is the same as hard decision, I have to really prove something. Okay, right. So it's impossible to prove. Well, actually we are not neglecting. So we are doing it differently in hard decision. What are we doing? Instead of using L4 in all its entirety, we are saying we will use only instead of using the small l's in all their real number complexities, we are only using one bit about them, right. When you do a hard decision using L4, what are you doing? Using R4, when you do a hard decision, you are saying I am only keeping one bit of information about the entire R4. Okay, here we are using all the bits. That is the difference between hard decision and soft decision. Okay, after you take one bit, you are still doing some processing like this. You are doing a syndrome decoding, right? And then only you are deciding. So there is some processing happening, but it is not the same as using the entire real valued information about R4. You are just throwing everything away. You are keeping only one bit of information. So for instance, if you quantize all the small l's to just one bit and run your bitwise MAP decoder, you might expect that to be the same as syndrome decoding, yes or no? Think about that. Okay, think about what that means. Okay, anyway, does not matter, but that's the difference between hard decision and soft decision. You are not using the small l's as real numbers, you are quantizing it to just one bit. You are saying whether it is greater than 0 or less than 0. Okay, that is the only thing I will use, I will not use anything else, is what you are saying. Okay. All right, is there a question?
Denominator E4 L2 plus L5.
So L5, so
L5 is it? It's not L4. Where is this? The third term. Okay, so luckily that does not change any of the statements I made about the properties of this expression, which are important. So I guess thanks for pointing it out.
Then we can also choose all zeros and replace LI minus L.
Yeah. So okay. So the question is, why did I choose all ones in the denominator? Why can't I choose all zeros? Okay, yeah, you can do the exact same thing. No, absolutely nothing changes if you do that.
not
Well, okay. So it depends on the code. So all those things are out there, I mean, so you can't really make a general statement based on which is the optimal thing to divide by. Okay, so that's difficult, particularly when your numbers are large, like 1500 and all. It's just you can give up. It's not possible to solve those problems. Okay, so what I'm going to do next, real quick, is to write a general expression for a general code, NK code. Okay, so it will mirror this expression very closely. So you will see how it works. It's not so difficult to write down. Okay, so if you have a general NK code. Okay, so one of the properties you can show is this following thing. If I define C I equals 0, oh no, I'm sorry, C, what am I saying? C conditional on Ci equals 0 as the set of all code words in C such that Ci is 0. Okay, one can show very quickly that this will be a subcode. Okay, so this will be a subspace. Okay, and you can also show, okay, it will be a subspace, and you can also show there are only two possibilities for its dimension. Okay, one is k itself, the other is k minus 1. Okay, so think about what it means. If it's k itself, what does it mean? The entire code has ith bit equal to 0, okay, which is a really bad thing to do. I mean, you should not do that. So if you assume that the code is such that no one position remains 0 all the time, then the dimension of this guy will be equal to k minus 1. You can prove it, it is not very hard to prove. Think about how you might want to prove it. There is a problem like this in the tutorial also, okay, so which has a solution, so you can check that. So the dimension of this subcode equals k minus 1 if you assume under some very mild assumptions. Okay, so what is the mild assumptions on code? On C. Okay, the mild assumption is basically that C is such that no one coordinate remains 0 all the time. Okay, so if that is the case, the dimension becomes k minus 1. Okay, so so why this is useful is, why is this useful in the bitwise MAP decoder expression? the numerator is controlled by code words of this form for capital Li, am I right? Set of all code words with Ci equals 0, and this tells you that it is exactly 2 power k minus 1. So what about the remaining guys? They will be in the denominator. Okay. So those guys in the denominator will also be. Okay. So this implies C such that Ci is 1, which is the set of all C belonging to C such that Ci is 1. Will this be a subcode? It will not be a subspace. Why will this not be a subspace? Yeah, all 0 is not there. Okay, so that's one way of saying it. Or you take two code words which have ith bit 1, you add them, what happens? Ith bit becomes 0. Clearly that is not in this set. Okay, it's not a subcode, but has size equals 2 power k minus 1. Okay, so that follows from the previous result. Okay, so this is true in general for any code. Most linear codes will satisfy this constraint. Okay, it does not matter whether I is the systematic position or parity position or anything. Okay, so for any position this is true, as long as you make sure this mild assumption on C is valid. Okay, so once you have this, you can very easily write down capital Li. This will be log. Okay, what should I write down? Log, there will be a summation over u in C such that ui is 0 or u in Ci is 0, whatever, the same thing you are writing. Okay, and then what should I write here? Okay, so I will write it slightly differently. Product I will say j such that ui is 0 e power Lj. Is that okay? Fine. Divided by, you will get a similar expression, but here you will have to put summation u in C, ui is 1 product over j such that, I am sorry, this is uj, no? Okay, uj equals 0 e power Lj. Okay, what is small Lj? Lj is 2 Rj by sigma square is the scalar LLR, this is the vector LLR. Is that okay? So that is a generalization of the previous one. Okay. So once again you can also do the general intrinsic extrinsic kind of thing. So you can show that this will be the same as Li plus log summation u in C such that ui is 0 and product j not equal to I such that uj is 0 e power Lj divided by summation u in C ui is 1 product j uj is 0 e power Lj. Is that okay? So here I have just pulled out the Li. So if you will see previously, if j equals I, clearly ui will be 0, so e power Li will show up in each of the terms in the numerator. So I can pull it out and write it in this form. Okay, so this is a very general form. This is called intrinsic LLR. So this guy is called extrinsic LLR. Okay, so this is the final vector LLR. Okay. So this is what channel is also called channel information. This is the belief or the probability or the LLR that the channel is giving you. Only the channel is telling you about the ith bit. What is this? This is from the code. Code, basically not just the code, from the rest of the rest of the bits in code. Okay, so basically it brings out how what Ci will make the rest of the code behave in a certain way. Okay, so that is what that brings out. Okay, so that is extrinsic to the ith received value. This is intrinsic to the ith received value. Okay, so you are combining what comes from the channel using the knowledge of your code, bringing it in and you are getting the answer. Okay.
Sir, in the optimal decoding, do we do it for all the bits or just the message?
For bitwise MAP. Okay. So that's a decision you can make. I mean, you can. Okay. So I have to answer that question very carefully, because if you are implementing the entire optimal decoder and complexity is not an issue to you, okay, 2 power k minus 1, okay, when k is 500, that's a big issue. But assuming the complexity is not an issue, it's enough if you do it only for the message bit. But what people do in practice is, like I said, they don't evaluate all the terms in the numerator and all the terms in the denominator. Okay, there is no hope of being able to evaluate all these terms. So you will start with some iterative process. Okay, you will iterate on it. You will find some terms and then you will further iterate, find further iterate, etc. When you do that, you will have to compute for everything. That is the difference.
But in general, like when we receive the message, when we message plus the code bits, I mean we take the message and also check. I mean, for example, CRC checks and all. We do the checks and then only we go to higher next level, right?
Yes.
In such case, it's necessary to decode even the parity bits, right? For example, if
No. Usually the way it will work is, see, the CRC will be outside. Okay, CRC will be on an outer block. The error correction will be inside. So your message itself will have a CRC check. So if the codec or the decoder is giving you a message bed, that will all not be independent. Okay, so that's the assumption that we make when we design decoders. But obviously that will be part of some IP packet. It will have header, it will have whatever. I mean, whatever it has will be there. Okay, and there will be some dependency. So it's assuming it's independent and all is an assumption, but usually works in practice. It's not a bad assumption, but you should be aware that CRC might be there already. So if at all CRC is there, usually it will be inside the message. You wouldn't put it on. I don't know if it's a good idea to put it on the entire block. If you do that, then you have to decode everything. Yes, you're right. Yes.
LLR. So which information is the strongest? This intrinsic or extrinsic, which drives me to decide something.
Okay, so these are all very difficult to say, these kind of answers. So the question was, which will dominate, small li or the other one? Okay, so you have to think about this very carefully, right? So it depends on how bad your channel is. Suppose your SNR is very high, then what's going to happen? Capital Li is going to dominate, right? So this, if at all it goes into error, it will be only very minorly in error and can be corrected. So that's what you expect. But when your SNR is bad or average, then small li also will not be very good. So you are really relying on everything to correct. Okay, but in general, as long as your SNR is decent, you will get good LLRs. But there will be some errors and you have to correct them. So the way to answer your question is, if the ith bit is received correctly, small li is probably going to be good. If the ith bit is received wrongly, then the extrinsic is the only thing you are hoping for, and it will be usually good. If your code is good and if it's supposed to work at that SNR, the extrinsic will be good. Okay, that's the way you have to think about the problem. Any other question? Hello. Okay. So the thing I want to point out is this structure for the vector LLR or the final LLR is very crucial. Okay, so it's kind of exploited in approximate computations. Okay, so you try to compute your intrinsic LLR accurately. There's no big deal in computing that. Okay, it's just 2R by sigma square. Anybody can do it. But the extrinsic, clearly you cannot compute accurately. Okay, so particularly when k is 500 and all that, it's very difficult. Okay, but one thing you have to pay attention to is, for different I, the extrinsic LLR computations will all be related. Okay, so it's not like you have to do the same computation over and over again. You can optimize it a little bit, but even if you do that, it's very hard. Okay, so it's difficult. If k is 500, it becomes 2 power 499. It's a very large number. Okay, so what people do is they try and approximate the extrinsic. Okay, so they see how well you can approximate in practice. Okay, so and your code has to be suitable for that. Is your code such that approximating the extrinsic is easy? Okay, so in all approximate soft decision decoders, okay, the main trick is to approximate the extrinsic LLR. Okay. In fact, the surprising part is in most practical implementations of these decoders, you will erroneously compute the extrinsic LLR. Okay, you will know that you're computing something which is not the extrinsic LLR. Okay, you can find that out very easily. Okay, but you will still go ahead and do it, because it turns out even if you erroneously compute it, it is good. Okay, it works out very well, because as long as the code is not really bad, it works out quite well for the kind of error rates that we want. Okay, so if you don't want like 10 power minus 40 block error rate, if you want like 10 power minus 6, which is quite reasonable, these kind of approximations and erroneous computations of extrinsic LLR is still good enough. Okay, it cannot be totally wrong, you can't just compute all that you want. There should be some sense in which the error is small. You should be able to say that if your block length becomes very very large, the error goes to 0 or something. You should be able to show that the error will go to 0 at under some conditions. If you can't do that, even if you do an erroneous computation, the extrinsic LLR is good enough and you get good answers. Okay, so that's at the heart of many of these approximations. Okay, so you compute the extrinsic and you will make errors, but you bound the error. You say the error is, in fact you don't even bound the error, you simply say the error is going to go to 0 if something becomes large or under some conditions, and then that becomes good enough. Okay, so I think, I can do more examples, but I think this example 6.3 example was good enough. So this kind of example is good enough. You can go and try the other bits if you want, you will get similar answers. It's not too difficult to see that. And one more thing I should point out is the bitwise MAP decoder and the ML decoder clearly does not agree here also. Okay, what do you do in the ML decoder for deciding the 4th bit? So it's kind of similar. Look at what's inside the exponent. Okay, so that is kind of what you do in the ML decoder, right? So you go and think about what it means. When you do correlations with all ones and all minus ones, it's roughly the what is there in the numerator. Okay, it's not you don't take the exponentiation and all that. Okay, so but one thing in the repetition code we saw that the ML decoder and bitwise MAP were same. So versus for this 6.3 code, clearly it won't be the same. Okay, it will be very very different. Okay, so I think we are running out of time, so we'll stop here. So what we have seen is optimal decoders. Then what we'll see in the next week. Next week we don't have class, no? Okay. So week after that, in the following lectures, what we will see is we will see ideas such as capacity and what is the best coding gain you can do. The notion of coding gain is something I will introduce in the next lecture, and that's very crucial in today's communication systems. And today you do error control coding or coding for coding gain. Okay, not really for correcting errors. That's the way to think about communication systems. Okay, so we'll stop here.
Any chance increased our error correcting capability?
So that's the thing of coding gain. I'm going to talk about it now, but you're saying error correcting capability. Okay, so those things are very hard to prove.
Because previously we were doing it in Hamming distance.
Yeah.
Now it's an Euclidean distance. So
okay, so let me point out one thing. So the error correcting capability will not really increase because of this. Okay, you can only correct so many errors without any ambiguity. Okay, so that is definitely true. And many of these decoders, ultimately their performance is bounded by minimum distance only when you go to really really low block error rates. But if you are not going to such low block error rates like 10 power minus 40, willing to settle for 10 power minus 6, 10 power minus 7, 10 power minus 8, then it turns out minimum distance does not control it too much. Okay, all right. Thanks.